Welcome to this week of the Chromatic Newton Search Seminar. So this time I'll be talking about spherical Witt vectors and the deformation theory. So I'll share my screen real quick in a moment. So this will be kind of a short talk, and in the next talk we'll see the construction of E-theorems. So that'll be what, and yeah. So this is meant to be a kind of a short talk, so kind of understanding things. Here's the plan. So I'd first kind of try to talk about the classical and spherical Witt vector constructions, right? So this is my notation. So instead of using bold W, so W plus would be my notation. That is something that I'm sticking to right now for this talk. We'll talk about a few properties of the spherical Witt vector, the deformation theory, and lifts, and a few things. And then we'll look at some tilting results. So, right. So let's begin then. So, right. So first, in order to talk about the Witt vector construction, first let's fix a perfect field. So fixing a perfect field F with characteristics a P, that is. So yeah, I won't like go through all the details, but I'll try to just motivate and talk about Witt vector, or about the theory of Witt vectors. So the theory of Witt vectors, it in a way, so it allows us to express this field F that we have fixed as a quotient. So let me write it down. Expressing F as a quotient. So this is, so explain what all this is, where this is the complete frame, where P isn't a zero divisor. And yeah, so this object that we have, so this is the ring of Witt vectors, which in fact is uniquely up to an isomorphism determined by the perfect field that we're fixed in, a perfect ring that we're fixed. F. Sorry, did I say perfect ring? Yeah, okay. Right. So okay. So I'll briefly talk about the abstract construction of the ring. So I'll just say it, and then will be so for our purposes, for in order to for construction of Lubin-Tate spectra. So we've seen Lubin-Tate theories in the previous few talks. So for our purposes, we actually want to generalize the construction. Right? So I'll just briefly go through the construction, just breeze. So the thing is that, so again, yeah, of course, I want to prove it. So the main reference for this would be, first, the main paper, apart from that, Blurie's electric homology. So let me say that from the outset, like if there's anything that is not complete or anything, we can find this in, I think, part 3, electric homology, part 3, Blurie. Right. So, right. As I said, I'm not getting the details. So now, as we have assumed F to be perfect, so turns out you can prove actually. So as F is perfect, you can prove that the relative potential complex so then using deformation theory, right? So I'm not going through all the details. So F can be uniquely lifted F can be uniquely lifted So N is greater than, right? And right. So and we get uh, ring of with vectors by taking the inverse limit over N. Inverse limits. I'm just writing few like all these like bunch of words. So because I'm not going to this detail, inverse limit over N. Right. So that's the way you construct. There are other ways of constructing it as well, but this works. So this is makes it a bit more compatible in a way. In um, right. So now let's begin by introducing some machinery. So we'll define both the classical and the spherical Witt vectors after this. So first, for that, we can introduce a bit of machinery. So first, so fixed X as a connective infinity ring. Suppose is a finitely generated idea. And then if we have a commutative diagram, so sigma, suppose something that will look like this. So we'll call this F. Okay, I'm not defining it. So this X naught. So similarly, we would also define the Y naught. This is the form. Right. So similarly, you also define that. Right. Where, of course, Y naught is a ordinary community. So we say that the sigma diagram exhibits F as an X thickening. So is that as an X thickening of no zero if two things Y is I complete, B second. Okay, not okay. Maybe I'll write it as three bits. So this diagram induces isomorphism of commutative rings. Something like okay. C. Yeah. Something like this. Then, moreover, so this is very important. So for connective infinity algebra Z over X, which is I complete. The following is so we'll see is a whole different purpose. This is right. Uh, so I'll just add this the functoriality as a remark. So this is actually so there is functoriality. Yeah. So suppose we have a something a community diagram. Let me draw this of connective Also, yeah, connected infinity rings. So let me draw this first. Oops. So you have something like this. And suppose, maybe I'll write it on this page. You have a commutative diagram. All these are connected. The infinity rings. So suppose uh, suppose suppose we have a okay. I think I should pause for a second in order to okay. I think that. So and okay. We have subjective ring of opposite. Something like this. Whose component. Okay. I think I need a few more seconds. I need to look at it. Think about this for a second. Yeah. So its component was did I just say component? It's composition has go. So it's called psi again. Okay, I think I missed something here. Yeah, as you can see, I missed the notation. So it's supposed to be, okay, I've kept the name this X, so X. Yeah. So that is what I was going to is a bit weird. And this would be X not. Composition as well. And yeah, I also did mention one of them. So I also assume that these X not and Y not are ordinary commutative rings. Right? I'll try this. Um, okay, so that's suppose now. Right, so now here's the tutorial. Suppose this so in this diagram, the outer rectangle. So suppose the outer rectangle exhibits F as an X thickning of F naught. So suppose the bigger rectangle, I don't know, is this oh, oops. Is this what do I represent? Now my tab skips and do that. Okay, I'll give it another shot. So, so suppose this, hope it's not that bad. Suppose the outer rectangle, so exhibits F as X thickening of F naught, and the yeah, and the upper square, that we have. So this upper square exhibits y dash as some, as we saw before, I completion of y. That should be. And the lower square also, the lower square exhibits this lower square exhibits dashes and x dash thickening. And so this is the functor actually. So, right. So now the main existence result for thickenings. See the theorem, main theorem. Also, I would give a proof for this. But yeah. So suppose that is a infinity ring. Then again is a finite lesion rated ideal, and it's can define so not to be. Suppose so this main theorem will be used for a classical Witt vector construction, or spherical Witt construction that we'll see. Yeah. So suppose Z naught is an algebra that's almost perfect. So Z module and the this Frobenius model that is flat uh, flat then if for a map so say from dash of commutative algebras such that the following diagram is a Poisson square then there exists a diagram and so this is the key result that theorem that we use actually that exhibits F as and Z as a Z thickening of the function. Also, this square is in the function. So this condition is said to be so when a map, when for a map F this happens, so then it is relatively perfect. It is said to be relatively perfect. Now, so yeah, so now using this, we'll see the classical Witt vectors construction. So it'll use the same notation. So Z, so just to make sure that I'll just scroll through this again. So remember Z is the connecting for engineering or the notation that we fixed is the Frobenius. Right, sure. So for this case, Z would be of integers or maybe and our idea is and then 0 is an FPR and our map is relatively perfect and is a perfect FPR. Right, so this is like equivalent thing that we have. If this is satisfied, then using the previous theorem, we can lift so flat zero Z is letting of continuation. Is that not? So yeah, maybe I could have been better with the notation. So the bold Z is for integers. Just the Z is the name of the. So maybe, but okay, let's stick with that. Flat Z algebra Z not right. That is complete with respect to this idea I and for which this Z algebra is the ring. Classically, this is the classical vector construction. So now, without further ado, I'm going to the spherical main. That's what we're interested in. So now, spherical vector. So again, we'll use previous theorem that we had. We'll use same notation and everything. Right? So now instead of Z, ring of integers, we're taking the sphere spectrum. Maybe. And again, we have this idea. Again, so things that we did the last case as well. Is the finite F. And a map is relatively perfect. Perfect. If and only if so, we have similar. Is only is a perfect image. So then again, so using the previous theorem, we have a lift, right? So right lift to a flat algebra says a dash. Which is complete. with respect to this idea. And for which so, right? So that's more good. Right. So this gives us the spherical with vector construction. So my notation, as I said, so still in the classical notation, but Dubey was so we get a function. And so let's call it adjoint, adjoint functor, right adjoint. That is also something that we use. See. So now let's see some important properties of the circular vector. And we'll go through the results and a few applications of these properties. Right? So now instead of this at all, I'm just taking, right, I'm just taking an arbitrary perfect. It's just Z. Periodically inclined. Well, I'll explain what that is. Second part can be described as spazier extensions. Yeah. Right. So yeah, I won't give a brief of all the results, but maybe the first few ones, the ones which are pretty straightforward and which previous results. First is a first lemma that is this is the first property that we have. It's the spherical vectors associated to a perfect FP algebra Z are spherical vectors. So they are periodically formally eta. So what does that mean? Periodically formally eta. That just means that. So the P complete potential complex just right. Expansions. So that is what I mean organically. Right? So okay, maybe let's go. So now, so in the previous, in the construction itself was spherical vectors. So in the from the construction, let me write this down. Yeah. Saw that we have a description like this by the perfect FP algebra Z. And write it as Z is a perfect. Right. So now we'll get something like this, right? That is, and that is. but we're not done. That's not it. I'll look at the P completed version, right? So now the thing is that so this is again, so the references for this, the reference is higher algebra actually. I think there's 7.6, 7.4 something. I'm sorry, I don't remember exactly. So I think the short you are also mentioned the proof, what section exactly. So just higher algebra is so the already completed of the total spectrum. So that is just be completed, but also vanishes. So that's the proof. So you can show that maybe I do not, but I do. So if the unit map R is numerically formally laid out, the deformation for any square zero extension, say, we call this from K to K dash. The map, the following map is an equivalence. Following map, so write this down. So again, that is with the notation. So this is the name. So we saw the description of the Spherical Witt factors, but the thing is that we have an analogous description of so we have the following lemma. The commutative algebra can be expressed was indexed tower starting at Z, where each one where the extension by suspension. By suspension. So using this really so that I few consequences actually. Again, I want to approve. So either for this lemma or the consequences that I'm talking about. I just list them. Yeah, it's not difficult to it's an exercise to think about. So this font commutes with arbitrary products. Satisfies decent commutes text. Functions. There's another, so now we have the following description actually of the essential image of this file. How can I? So you use all of these to for construction materials. That will happen for next essential. So lemma. Okay, maybe just idea. So commutative algebra Z. There's and the essential image. Then only yeah, equally formally down. Both. So proof idea. Exactly. The idea is to just exhibit it. Just try that. So let say L as a limit for the square extension. So this is the idea. Right. Right. So after you've done that, then Z. Oops. So as Z is we can do normal down. So we have what is the bonus? L. So now moving on to constructing multiplicative lifts for the so let's begin with the construction. The construction of multiplicative spherical impacts. Spherical multiplicative. So Z is a perfect algebra. So if Z is reacts vertically. So star of there is Z star. So Z star is the I don't know how do I put this on non-zero 0 elements of Z the multiplicators. Yeah. So that's Z star. So the map of map between perfect FP algebras, right? So right. So then the thing is that okay, so then if we apply the functor and okay, but there's a thing that we'll be using, so maybe explain this first. So suppose I don't know, so okay. So discrete integer on which p acts invertibly. And we have the following equations, and this is something that we can do this. You can see what I mean. So we'll apply the function and use this fact. So then we'll get something like this. So we'll get a map. Right. Which is the spherical with so now we'll see what's some tilting results, deformation, maybe deformation. So to find the right adjoint to the functor, this is the tilting functor. Right. So here's the code representativity is a lemma. The tilting functor is so this is very useful. We'll see as we see in the next few. So this is the thing actually that is see is code into the algebra. Okay, let's put this. So this follows from the so the previous equivalence actually that I kind of digressed a bit into. So this equivalence right here. So actually use this actually. So using this previous equivalence, so let's see this again. Just because I seem to forget this. Okay, yeah. So using this, please point out if I write this. Yeah, I think this is using this equivalence, the thing that I have explained. Oops. Right. So using this and the fact that the elementary fact that this represents the underlying perfect free algebras. Right. So that is it. That's a question. So schedule at the moment. So okay, so using for representativity of the tilting functor, we will have the following result. So given a square feet, square zero extension, so maybe into a dash. The map, so you can apply the functor. So this is an isomorphism. So again, I will just I won't put this. I'll just give you the idea. So use the fact. So the fact co-representability as I said, it's co-represented. Use this. Will be done. And another lemma. From sense the maps of the span. Shouldn't the span? So it looks something like this, I believe. So equivalence is provided. Right. Let's also kind of go through the idea of the proof. So this that we have, and this is like, so this follows from the fact that follows from the oops, not this one. Sorry. So, okay. Then, so the positive tower is a tower of square zero extensions. And then using the previous lemma would be, so again, so using the previous lemma would get that. So for the second one, is an equivalence. Yeah. That's it. Another important lemma, but this time again, we should go through the details. So again, suppose that it is and x. So fine. So okay, this is not bold set. It's just a well, maybe I should stop it. Stick with that. So it is a class such that so it is complete. Then there exists an equivalence. So something yeah. So I've already seen okay. Maybe yeah. Yeah, I was thinking of briefly talking about moving trade theories rather than position maybe to do that. So yeah, I am almost done actually. But before that, so now the next part would be to so now we are gradually moving towards the construction of E theory. So there are yeah, there are a few details and things that we'll be using actually that we've seen before, that we've been exposed to before, without mention. So before that, actually, so okay, actually don't have anything planned after this actually. So let's see something that I think is yeah, that is also something that you may see in the next talk also. But let's do that. So let's do that because Hawkins-Phillips theorem and Willie's work with that. So try and write sequence Hawkins Miller. So F is a perfect field. Characteristic B. And it is a formal group of height and finite n. Right. So given all this, there exists an even I can share the paper because the paper actually. Even periodic Km local commutative algebra such that can be identified with the Lorentz tree parameterizing deformation. So Louis thought of a generalization of this actually. I'll just write this as a theorem. The few results. So this is just meant to be more of a prelude or something of that sort, right? From the next talk. I'll just try. Where you have functor. Notation, but so this was Lowry's generalizations. Okay, let's list a few properties, the ones that come to my mind. That Prakash, I know that this is fully faithful. So okay, maybe right. This is a prelude theory construction. Fully faithful. And now okay, so this is a formal group of right and it's a perfect FP algebra. It's K and local ones that are evident. I'm just writing it down and you can create period. The essential image of what's image of consists okay, there's another condition that I should have listed before this one. So any sequence star lifting the Hasse variance. So now comes the fourth part. So yeah, I believe the next one, speak will explain it. Maybe also do this. The essential image of this functor that will structure consists of commutative algebra satisfy these two and three, for which so remember this is the language idea which spread out of locals of height data when it's perfect. So yeah, there are a few more properties also. I think which are listed, which are there in the paper actually. And I go to which one beyond. But yeah, these are the ones that I have in my mind. See right at the back. So maybe I'd like to stop it here. So like, thanks a lot for listening. And maybe start the recording here. All right.